All right, how's it going, guys? In this video today, we're going to be going over 8.2, day 2, and we started with the warm-up here. It's a little review of what we did in 8.2, day 1. So if you haven't tried it, take a second to pause the video and do it before I start on it. Okay, so here we're told we need to solve this polynomial by finding all the roots. And we have the polynomial that we have is x cubed plus 125 equals 0. So we need to factor it out and find all the zeros of this polynomial. So we see that it's a sum of squares, so we can use our factoring patterns to factor it out relatively quickly. So we get x plus 5 times x squared minus 5x plus 25. That's what you get when you factor out x cubed plus 125, and all of this equals 0. And what we're going to do now is we're going to set each factor equal to 0, and we're going to solve for x. So for the first factor, x plus 5, we set that equal to 0, we get x equals -5. So that's 1 0 of this polynomial. And for our other polynomial, we have x squared minus 5x plus 25. We have that set equal to 0, and we need to solve for x. We cannot factor this out any more than it already is, so our only choice here is to use the quadratic formula, right? Because there's no factors of 25 that add up to give you -5, so our only choice we have to solve for our x is to use the quadratic formula. So the quadratic formula is -b plus or minus square root of b squared minus 4ac all over 2a. So we get 5 plus or minus the square root of b squared, which is 25, minus 4ac, which is 100, all over 2a, or just 2. If we solve this out, we get 5 plus or minus the square root of -75, all over 2. We can take out that negative inside the square root and get 5 plus or minus I square root of 75, all over 2. And now we need to find the prime factorization of 75. So let's do this up here in the corner. For finding this, the prime factorization of 75, we need to break this down into all prime numbers and pair up any of the same numbers. So in this case, we have one pair of 5s, and we're left over with a 3. So what we do is we take out that 5 that we grouped up, and we'll leave the 3 inside of the square roots. So our x values from the second factor that we had will be 5 plus 5i root 3 over 2 and 5 minus 5i root 3 over 2. And if we think about what we said in the last video, in the last day, we said that the total amount of zeros you have to equal the total degree of the whole polynomial. And the total degree of the polynomial is 3, and we see we have 3 zeros. X equals -5, and x equals 5 plus 5i root 3 over 2, and 5 minus 5i root 3 over 2. And that's called the fundamental theorem of algebra, and we meet the fundamental theorem of algebra, so we have all our zeros. So anyway, let's go ahead and get started with the notes for the day. Here, for today, what we're going to be doing is we're going to be writing polynomial functions from the zeros. So we're kind of going to be doing the opposite of what we've been doing for the rest of this module. We're going to start with our zeros, and we're going to go back to our standard form of the polynomial. So the irrational root pairs, a plus b root c and a minus b root c, are called irrational conjugate pairs. The complex root pairs, a plus bi and a minus bi, are called complex conjugate pairs. Irrational and complex roots always come in pairs because of the plus or minus in the quadratic formula. And what that means is that anytime we have a root of something in the form a plus bi, we must also have the root a minus bi. You either have both of them or you have neither of them. You cannot have just one. And that's the same thing with a plus b root c and a minus b root c. You either have both of them or you have neither of them. And that's because whenever we actually get something in that form, we get it in that form because we're using the quadratic formula, because we're taking the square root of a variable. And every time you take a square root of a variable, you have to put plus or minus. and that's why they have to come in pairs. All right, and that's exactly what the irrational root theorem and the imaginary root theorem say. It says if a plus b root c is a root of a polynomial, then a minus b root c must also be a root. And the imaginary root theorem says if a plus bi is a root of a polynomial, then a minus bi must also be a root of that same polynomial. So they're both zeros of a polynomial, or neither of them are zeros of a polynomial. So now we're going to name the conjugate pairs. So we have 3i, its conjugate pair will be negative 3i. Next, we have 9i, its conjugate pair will be positive 9i. Negative root 5 becomes, it doesn't become root 5, but its conjugate pair is the square root of 5. Square root of 7, its conjugate pair will be negative square root of 7. So now we have 2 minus 5i root 3. Its conjugate pair will be 2 plus 5i root 3. And then we have negative 5 minus 4i root 2. Its conjugate pair will be negative 5 plus 4i root 2. And something we can realize with these last two examples is that the only sign that we're changing is the one right next to the I and the square root. That's the only sign that changes between the conjugate pairs, and that we're not going to be changing the sign of the coefficient before it. So right here we have negative 7 plus 8i. That's going to be negative 7 minus 8i. That's its conjugate pair. We do not mess with the first term. We only mess with the sign in front of the I or the square roots. So 11 minus 8i becomes 11 plus 8i. Okay? So let's go ahead and do some examples of what we said from the beginning. We're going to start with our zeros, and we're going to work back up to our standard form polynomial. So in number 1, we're told here the zeros 5 and 4, but 4 has a multiplicity of 2. So first we're asked, do we have any additional roots? In this case, we don't. Those are all the zeros they gave us, so those are all the zeros we're going to use. Next, we need to figure out what our final degree should be. The final degree of a polynomial should be the same as the amount of zeros that we have. And number 1, you see we have 3 zeros. We have 5, and we have 4 twice. Remember, multiplicity means how many times that 0 is happening. We have a multiplicity of 2, that means 4 is happening twice. So we have 3 zeros, 5, 4, and 4. So what we're going to do now is we're going to set each 0 equal to x, and we're going to solve it, or should not solve it, but rather we're going to set them equal to 0. Remember, all factors have to be equal to 0, and that's how you get it. That's how you get your factor. So we're going to minus the 5 over for the first one. You get x minus 5 equals 0. Next, we have x minus 4 equals 0. And then x minus 4 equals 0 as well. Okay? And these are what our factors will be. Remember, each factor has to be equal to 0. So we set each factor equal to x and then solve it for 0. That's what we get. Those are our factors. And all we have to do now is multiply them all together to get our standard form of the polynomial. So we have x minus 5 times x minus 4 and x minus 4. Or just simply x minus 5 times x minus 4 all squared. X minus 4 squared is actually a perfect square trinomial. So we can FOIL that out really quickly. And it should be x squared minus 8x plus 16. That's just from your factoring pattern. If you don't have that memorized, you could just FOIL it out normally. You get the same thing. But knowing your factoring pattern will make this much, much quicker. And now all we're going to do, that should be x minus 5, not x minus 4. So we have x minus 5 times this polynomial. And now what we're going to do is multiply them both together. So we get x cubed minus 8x squared plus 16x minus 5x squared plus 40x minus 80. All right, we multiplied x minus 5 with x squared minus 8x plus 16. And now we're going to add like terms. There's only one x cubed, so we can bring it down. Negative 8x squared and negative 5x squared add up to negative 13x squared. 16x and 40x add up to 56x. And we don't have any other constant term other than negative 80, so we can just bring it down. And this right here is our standard form of the polynomial with the zeros 5 and 4 with a multiplicity of 2. Okay? So let's go on to number 2. With number 2, we're actually going to deal with square roots. So first we need to figure out, do we have any other additional roots? In this case, we do. Remember, if we ever have something with any zero with a square root in it or an imaginary number with it, you're going to have additional roots with it. You have to have both zeros of the pair. So in this case, you have 3 plus 2 root 7, and its conjugate pair is 3 minus 2 root 7. You have to have both, or you have to have neither. You cannot just have one. So we're going to add the other one with it. So our final degree should be 3. These are all our zeros, the 5, 3 plus 2 root 7, and the 3 minus 2 root 7. Those are all our zeros of this polynomial. We have 3 of them, so our final degree should be 3. And we're going to do the same thing we did before. We're going to set each 0 equal to x and solve it for 0. 3 plus 2 root 7 and x equals 3 minus 2 root 7. So for the first one, that becomes x minus 5 equals 0. For the second one, that's x minus 3 minus 2 root 7 equals 0. And x minus 3 plus 2 root 7 equals 0. So now I need to multiply all of them together. X minus 5, x minus 3 minus 2 root 7, and x minus 3 plus 2 root 7. So I'm going to multiply the last two polynomials together first. And I'm going to do that in a box just because I can keep everything a little more organized, a little more neat, and I won't get lost multiplying with my square roots. Okay? So I'm multiplying 3 terms in the first polynomial with 3 terms in the second one. So that means this needs to be a 3 by 3 box. Okay? And I'm going to put my first polynomial that I'm multiplying on the top. So x minus 3 minus 2 root 7. And the second polynomial that I'm multiplying on the side. So x minus 3 and positive 2 root 7. So I get x squared on the top left, and then negative 3x, and negative 2x root 7. And then negative 3x, positive 9, and a positive 6 root 7. And then 2x root 7, negative 6 root 7, and 2 root 7 times negative 2 root 7. What we're going to do is we're going to multiply the coefficients in front of the square roots first. So 2 and negative 2, which is negative 4. And then we're going to multiply the square roots together. Root 7 times root 7 is just a positive 7. Negative 4 times 7 is negative 28. So that's what we get in our last box. Okay? So now we're going to add like terms, and we'll get our polynomial from multiplying those two terms together. So x squared comes down. There's no other x squared term. Negative 3x and negative 3x add up to give me negative 6x. Next, I have negative 2x root 7. That with positive 2x root 7 cancel each other out. They're the same number, except one's positive and the other one is negative. So if you add them together, they cancel each other out because they give you 0. Next, I have 9. 9 plus negative 28 is negative 19. And last, I have 6 root 7 with negative 6 root 7. Again, they're the same number, except one is positive and one is negative. So if you add them together, it gives you 0. They cancel each other out. So those are gone. So this is what I'm left with. And now I have to multiply that with my 0 I have up here, which is x minus 5. Okay? So now I'm going to multiply x squared minus 6x minus 19 with x minus 5. So x squared times x is x cubed, then minus 5x squared minus 6x squared plus 30x minus 19x, and finally plus 95. All I need to do now is add like terms. X cubed goes down, there's no other x cubed term. Negative 5x squared and negative 6x squared add up to negative 11x squared. 30x and negative 19x add up to positive 11x. And lastly, the positive 95, there's no other constants to add with it, so I'm just going to bring it down. And finally, that is our standard form of our polynomial with the zeros that we started with on this problem. So that's a really long way to do it. There's actually a shorter way to do it. I just want to show you guys, I guess you can say the normal way to do it, but there is a much quicker way to go about it. All right? So I'm going to go ahead and erase this page, and we're going to start it over. So the quicker way to do this, or rather before we go into that, let's fill out our additional roots. 3 minus, let's actually do this in blue. 3 minus 2 root 7, and our final degree, we already said, should be 3. So the quicker way to do this is that we're going to set x equals 5 if x equals 3 plus 2 root 7. We're only going to set x equal to one of the conjugate pairs. All right, we have one conjugate pair here, 3 plus 2 root 7 and 3 minus 2 root 7. We're going to set x equal to only one of them. All right, so we're going to ignore the other one, and it doesn't matter which one you choose. You only need to choose one of them. In this case, I'm going to go with 3 plus 2 root 7 because that's just what they gave me. So if x equals 5 and x equals 3 plus 2 root 7. So x equals 5, I'm going to treat it the same way. Just make it x minus 5 equals 0. And for x equals 3 plus 2 root 7, what I'm going to do is I'm going to square it. But to make my life a little easier when I'm squaring it, is I'm going to move the 3 over. Or in other words, I'm going to isolate the square root or the imaginary number, whatever conjugate pair you're using, isolate the square root or the imaginary number. So I'm going to minus the 3 over. So we get x minus 3, and that equals 2 root 7. So the square root is isolated. So now I'm going to square both sides. And when I do, I see x minus 3 is a perfect square trinomial. And that's why we isolated it, because I can get it as a perfect square trinomial and FOIL it out much quicker than trying to FOIL out 3 plus 2 root 7 squared. Right? So it just becomes a little easier if you isolate the square root or the imaginary number. So we get x squared minus 6x plus 9, and that equals 2 root 7 all squared, becomes 2 root 7 times 2 root 7. So you multiply the coefficients first. So 2 times 2 is 4, and root 7 times root 7 is just 7. Or I get x squared minus 6x plus 9 equals 28. So I need to set this equal to 0 now. So minus 28 on both sides. And I get x squared minus 6x minus 19 equals 0. Okay, and if you guys remember, when we did the box and when we finished with it, we got that exact same thing. X squared minus 6x minus 19. All right, so there's just a much quicker way to figure out the whole box without multiplying the two polynomials with 3 terms each, right? Just a much quicker way. So now we're going to treat this like we did before. We have x minus 5 and x squared minus 6x minus 19. So we did this exact same multiplication before. That was the last thing we did when I did this problem the first time. So I'm not going to do it again, but you just multiply it out like we've always done before, like we did all year long. And when you do, you get x cubed minus 11x squared plus 11x plus 95. And that's exactly what we got before. It's the exact same multiplication we ended with when we did this problem the first time. So you should get the exact same standard form polynomial. Okay? So let's go on to number 3. And we're going to see how that little shortcut method works with i's. You're going to treat the same way, but we're going to see how it works. So we have the zeros 2, -3, and 1 minus I. Do we have any additional roots? We do. Remember, we have to have both terms of the conjugate pair. We have 1 minus I, and its conjugate pair is 1 plus I. So we have to have both zeros. Okay? If you have 1 0 of the conjugate pair, you have to have both. So our final degree of the whole polynomial should be 4, since we have 4 zeros. 1 plus I, 1 minus I, 2, and -3. So we're going to do the same thing we did before with the little shortcut method. We'll have x equals 2, x equals -3, and x will only equal 1 term of the conjugate pair. So I'm going to say 1 minus I, just because that's what they gave us. It doesn't really matter. You do the same exact thing regardless. So we're going to solve the first two for 0. X minus 2 equals 0, and x plus 3 equals 0. And now for x equals 1 minus I, we have a conjugate pair. We want to square it. But before we actually square it, I want to make my life a little easier and isolate the imaginary term. So I'm going to minus the 1 over first. So I have x minus 1 equals -I. And now I'm going to get rid of that I by squaring everything. Okay, so x minus 1 squared, that's a perfect square trinomial. X squared minus 2x plus 1. And that should all equal -I squared. So we have -I times -I. That gives you a positive I squared. And I squared, if you guys remember from, I think it's like module 4, module 3, I squared equals -1. All right? So now we're just going to add the 1 over to set this factor equal to 0. And we get x squared minus 2x plus 2 equals 0. So now that we have all of our factors, we're going to multiply everything together. So we have x minus 2 times x plus 3, and x squared minus 2x plus 2. I'm going to leave that on the side for a bit. So I'm going to multiply x minus 2 and x plus 3 together first. So when I do that, I get x squared plus 3x minus 2x minus 6. I add like terms, x squared plus x minus 6. And I'm going to multiply that with the x squared minus 2x plus 2 that I got before. So you can put this in a box if you like to, or you can just multiply from over here, whatever you're more comfortable with. You'll get the same thing regardless. I'm going to multiply from here. So x squared times x squared is x to the 4th, and minus 2x cubed plus 2x squared plus x cubed minus 2x squared plus 2x minus 6x squared plus 12x minus 12. Okay? So now that I have everything all foiled out, I'm just going to add like terms. I'm going to bring down the x to the 4th term. Since there's no other term here and raised to the 4th power, I can just bring it down. Next, I have -2x cubed and positive x cubed. Those add up to -x cubed. The 2x squared and the -2x squared, they add up to 0x squared, and I'm left with this -x squared around the end over there. So -x squared. Next, I have 2x and positive 12x. That adds up to 14x. And lastly, I have that -12. I can just bring it down. So that's my standard form of the polynomial for number 3. So there's still 2 more example problems. I do want you guys to try them out yourself. So I want you guys to pause the video, take an attempt at it, try it, and I'll post the answer up in a bit. Okay, so this is what you should have gotten with number 4. So we did the little shortcut method we talked about in the past 2 slides. We have x equals 2, x equals 2. Since we have a multiplicity of 2, we have that twice, and x equals 3i. So for the x equal 2's, I'm going to set them equal to 0, so -2 on both sides. I get x minus 2 equals 0 and x minus 2 equals 0. For x equals 3i, I don't have to move anything around since the I is already isolated. So all I have to do is square both sides. And when I do, I get x squared equals 9i squared. I squared is -1. So 9 times -1 is -9. So I get x squared equals -9. I can add the 9 over, and I get x squared plus 9 equals 0. After that, I just need to multiply x squared plus 9 with x minus 2 and x minus 2. And when I do, I get x minus 2 squared times x squared plus 9. X minus 2 squared is a perfect square trinomial. And when you multiply those two together, you get x squared minus 4x plus 4 multiplied with x squared plus 9. And then when you multiply those two together, this whole thing right here is what you get when you FOIL them all out. And when you add like terms, you should get what's over here in this box. X to the 4th minus 4x cubed plus 13x squared minus 36x plus 36. Okay? And let's do the same thing with number 5. Pause the video, attempt number 5, and I'll post the completed answer in a second. Okay? So here's number 5. We have 4 minus 7 root 2 and -1. We do have an additional root of 4 plus 7 root 2, so the final degree should be 3. If we're doing the shortcut method we've talked about, we have x equals -1. That's the first square root, the first root, and then we have x equals one of the two zeros in the pair. So I just went with 4 minus 7 root 2, since that's what they gave us. So when I set x equals -1 equal to 0, I get x plus 1. And for the right side, I'm going to isolate the square root first, so I minus the 4 over, and then I took the square of both sides. And when I did that, I got x squared minus 8x plus 16. When I take the square root of -7 root 2, you get 49 times 2, where I multiply the coefficients first. -7 with a -7 gives you the 49. Root 2 times root 2 gives you a positive 2. So you end up getting positive 98. I minus the 98 over, and I get x squared minus 8x minus 82 equals 0. And I'm going to multiply that with the x plus 1 I got before. And when I do, I get this whole thing right here. And when I add like terms, I finally get this standard form polynomial right here. X cubed minus 7x squared minus 90x minus 82. And that's the standard form of number 5 on the notes. All right. Other than that, guys, there's no other notes I need to go over. Hopefully this video helped.